our today's very interesting topic is Electrify Everything, Everywhere, All at Once. Moderator for this session will be Mr. Reggie Pillai, President ISGF and Chairman GSEF. And presenter for this topic today will be Mr. Michael Barnard, founder, The Future is Electric. ISGF's fortnightly webinar series presented by Mr. Michael Barnard aims to explore electrification's ability to cut primary energy requirements in half and minimize the amount of low carbon energy that must be produced. From transportation to heating to industrial solutions, electrification is the path to an efficient, inexpensive, and decarbonized future. Trillions of dollars will be spent on decarbonization in the coming decades. Much of it will be spent unwisely, and much of climate action must be taken in nations that are not developed and affluent yet. The short list of climate actions that will work is a set of material Mr. Michael Barnard has spent 15 years developing, researching each major problem area and the proposed solutions for it. He assesses each with the triple filter of technical viability, economic competitiveness, and human acceptability. Countries that embrace and lean into the short list will be more affluent, more resilient, healthier, and coincidentally do more for climate action. Countries that don't will suffer significant economic headwinds in the coming decades. Before starting the webinar, I would like to announce a few important informations, requesting all the participants to kindly mute themselves during the webinar. And we request if they should not unmute and turn on their videos while the speaker is there, while Mr. Michael Barnard or Mr. Pillai are speaking. If you have any questions, you can type it in the chat box and we'll be taking them in the end. Without any further ado, I would like to request Mr. Reggie Kumar Pillai, President ISGF and Chairman GSEF, to the stage, who will be also moderating today's session. Over to you, sir.
Good morning, good afternoon, good evening to all the participants from around the globe. As we move forward, we expect more people to join. And I thank Michael for agreeing to join this webinar series. And he had done painstakingly 15 years of research, detailed studies, not just research, detailed study on each and every topic which we hear today on decarbonization. So as most of you know, 151 countries have already signed the Paris Agreement. They have more than 170 has signed the Paris Agreement, and 151 of them have a net zero target varying from 2045 to 2070. And out of which 130 countries, the last COP in Dubai, pledged that they will triple their renewable energy generation capacity, and they will also double their energy efficiency by 2030. These are all short-term targets. By some estimates, about 2 billion machines which are today running on fossil fuel are likely to be electrified in the next 3 to 4 decades, which necessitate the electricity generation capacity to be tripled. And what we built in last 130, 140 years, we have to double it in next 30 to 40 years is a huge challenge, particularly in countries where huge potential of renewable energy is there. New transmission and distribution lines need to be built for evacuation of energy from the new solar farms, wind farms, including offshore wind farms. And one estimate which BNEF made, Bloomberg New Energy Finance made last year, November 2023, it says that about 80 million kilometers of new transmission and distribution lines need to be built in next 25 years with an estimated investment of $21 trillion. This is equivalent to 80 million kilometers, is almost equivalent to the existing grid, global grid, which we built in last 130 to 140 years. It's a huge challenge facing us. We may find that 21 trillion, but materials and people to do that job, and also the policy and regulatory support for this is extremely challenging. We need to find new ways of doing things. At the same time, the steep, you have all witnessed the steep price decline of solar, wind, and also of batteries. So this has actually taken us to a era of energy poverty alleviation globally. So solar energy today at 3 cents per kilowatt hour in most part of the world, in some places even less, is the cheapest form of energy humankind ever had. And we expect the efficiency of solar panels to double in next decade, and also prices to come down by anything from 50 to 70%. As far as the storage is concerned, in January this year, CATL, the world's largest battery manufacturer, they already announced that the cell which they are selling at $85 per kilowatt hour is going to be $56 per kilowatt hour in the second half of 2024. We expect by end of this decade the battery prices to be less than $30 per kilowatt hour at cell level. These are all going to bring into a revolution of electrifying and battery plus wind plus solar, and that is going to be the future. And without taking much of your time, I hand over to Michael for this interesting presentation. Over to you, Michael.
Thank you, Reggie. Thank you to the India Smart Grid Forum for inviting me to assist India in my tiny way to thread this needle of decarbonization and growing your economy. It's a great privilege. The presentation I'm going to do is a deep dive into one of the segments of the material that I presented at the India Smart Utilities Week. Unfortunately, that I ended up at the very end of the day competing with appetizers and cocktails. So I suspect the room was a little less full than it is today. So without further ado, let's start moving into it. This is the short list. For those, Reggie, I believe that there is a video of that presentation available from ISGF. I encourage people to go and review that, but it's also available on just by searching for me on Forbes for the short list of climate actions that will work. But today we're going to talk about electrify everything. And specific, as we look at this list, over the next 6 months or so, every couple of weeks, we're going to do another webinar and discuss each of these points. And so we'll explore these and explore them in context of India. And please ask tough and challenging questions. The value I'll get from this with tough questions is immense. So as I did in that presentation, I apologize for not using India's energy flow diagrams, but instead using the United States energy flow diagrams. The reason for that is very simple. The US energy flow diagrams, while still imperfect, have the most clear visualization of the amount of energy we waste in our economies. Roughly 2/3 of all the energy which comes in on the left goes into waste heat, entropy, on the right, instead of to actually useful energy services. And this is almost entirely energy waste heat from burning fossil fuels. If we consider a pathway, for example, from wind energy into electrical generation, there's virtually no rejected energy from that pathway. As we consider the pathway of those going into residential lighting and heating, there's virtually no loss of energy through that. And so most wind energy and solar energy goes directly into energy services, things which drive our economies forward and give us greater comfort and greater affluence. And so by contrast, we consider petroleum as it comes through into transportation. 80% of the energy in petroleum goes into rejected energy. Very little goes into here. This gives us a tremendous opportunity. It gives India a tremendous opportunity as a developing country. So let's take a couple of examples. This is material created by Dr. David Saban, a mechanical engineer in Cambridge and founder of the International Center for Sustainable Road Freight. He's a founding member of the Hydrogen Science Coalition to bring sanity to some of these discussions. But as you can see, one of the clear technological advantages for especially colder climates and the colder parts of India is that you get a bunch of heat from the environment, or in the case of air conditioning, cold from the environment, and move it into stock. So you need 1 unit of electricity to get 3 units of heat. Now, that sounds great for home and residential heating, but it's especially important in India's context for industrial heating. 45% of all industrial heat energy requirements are below 200 degrees Celsius. And we now have heat pump technology, as well as heat recovery technologies and heat storage technologies that allow us to provide 200 degrees Celsius heat and steam for industrial processes, for food processing material and the like. This gives us a tremendous opportunity to electrify and leapfrog and reduce our expectations about burning fossil fuels in order to achieve our industrial and food requirements. A theme through this set of presentations, because hydrogen is such a hyped technology right now, and it's hyped in India as well. I know there's a bunch of announcements in the past few months about hydrogen as a energy pathway in India. The same energy pathway would require 6 times as many renewables to generate electricity, to generate green hydrogen, to transport green hydrogen, to burn green hydrogen, to achieve the same heat value outcomes. So hydrogen as an energy carrier, as opposed to electricity, is 6 times less efficient. And so hydrogen, back to that rejected energy thing, would increase rejected energy in our society. And that means you have to build a lot more generation in order to use green hydrogen for energy purposes. This doesn't mean green hydrogen isn't absolutely necessary for decarbonizing the things that it's required for, such as ammonia fertilizers, but it does mean that we should be very leery about it, considering it for any energy pathway. Similarly, blue hydrogen for heat, taking natural gas or coal gas and doing carbon capture, well, the carbon in the methane is 45% of the energy content of that fossil fuel. So we're throwing away 45% of the energy, and then we're using energy to do that. So we're throwing away half the energy in an already high waste fossil fuel pathway. So once again, we're doubling rejected energy. This isn't an efficient or effective way to run a society if we have alternatives. Now, in context of all the heating options, one of the forms I created a couple of years ago to help start exploring some of these ideas was a quadrant chart. And the quadrant chart had 4 quadrants. It had a sexy versus meh, the meh being, kind of boring, but maybe it works, maybe it doesn't. But practical versus foolish. And the stuff that makes sense is in the practical column. The stuff that doesn't make sense as we move forward is in the foolish column. And there's a lot of hype, and there's a lot of attention paid to the stuff in the sexy column, the sexy row. And there, generally speaking, isn't nearly as much hype or enthusiasm for the stuff in the bottom row. So as we look at this, there's a lot of stuff like concentrating solar power, which looks really attractive and decorates a lot of articles, but doesn't really work compared to photovoltaics. A lot of discussion of hydrogen for heating and hydrogen for industrial heat, But as I pointed out, the rejected energy of using green hydrogen or blue hydrogen for industrial or domestic heating is extraordinary. Of course, one of the things that worked out really well globally, as it turns out, is cooking with gas. It was a advertising jingle. Now people are using induction stoves, and they're much more efficient and much better for indoor health. As we get down to the bottom low, there's foolish stuff that we have to persist for as little time as possible. That's use of industrial coal and gas for furnaces, industrial gas burners. Those things are currently kind of boring staid participants, but they're all significant portions of greenhouse gas emissions as well as air pollution. And once again, they're less efficient than the alternatives, the electrified alternatives. So get over into the boring stuff, heat pumps, induction stoves, and you see that just the sheer number of different technologies here, including plain old boring insulation. These are indicative of the sheer variety of electrified heat solutions that we have. So there's almost no area of heating requirements that cannot be met with electrification. It is a matter of delivering enough electricity in some cases in the right way. Now, the electric arc is interesting for India because India is currently the second biggest manufacturer of steel in the world after China, about a tenth of China's output as of 2022. Now, that's electric arc furnaces are a key part of the decarbonization strategy for steel because they can take new steel products like ones made with hydrogen or electrolysis from iron and then make new steel, or they can take scrap steel and make new steel. In my projections of the future of steel manufacturing will be at about 75% of supply of steel coming from scrap steel, some of them from the almost 1,000 ultra-large crude carriers still plying our oceans, and much of it from the fossil fuel infrastructure, and only 25% new steel. So electric arc furnaces become very important. Electric plasmas are very interesting. But we have all the solutions we need. District heating and cooling systems are key, and I know that India has a lot of those. When we look at transportation, that big petroleum waster, we have a tremendous efficiency gains. Now, this is by Transport and Environment, a European organization. It's an infographic provided to give context. And while the debates, from my outside perspective, I have not seen the debates as strongly. What I've seen is that certainly you're still exploring hydrogen for transportation. You've bought some small hydrogen locomotives for some legacy tourist routes, is the way I would describe them, in scenic parts of India. But dominantly, at least in rail, India is going exactly the right direction. You're electrifying, you're approaching, I think the intent is 100% electrification. I'll get a bit more into that and what a great global leader you guys are. Power to liquid is an interesting one to bring out as well. Now, once again, power to liquid, make green hydrogen with electricity, gets carbon dioxide from somewhere, put them together in a common industrial process, like Haber-Bosch for ammonia, and then distribute and put them in. But once again, 73% efficient, 13% efficient at turning electricity into forward motion. A power to liquid solution, once again, increases rejected energy in a society, maximizing and multiplying the amount of renewable electricity you have to manufacture. It's anything where any pathway that goes from electricity to an end electric use case as efficiently as possible will always be cheaper operationally and from a maintenance perspective. So another sexy versus meh chart. There's some fun stuff in here. Up here in the upper right-hand corner, there's silly things like maglev trains. There's only, we've probably all read about them, but there's only 60 kilometers of operational magnetic levitation trains in operation after 70 years. Hydrogen cars are literally falling off the market. The numbers are plummeting because it doesn't make any sense there. Elon Musk's Hyperloop is a complete and utter distraction. E-fuels, once again, back to that transport and environment thing, only 13% efficient at turning green electricity into forward movement. There's weird EVs like the Aptera. India is one of the few places where three-wheeled electric road vehicles make sense. And some of that is legacy regulation related to a specific province in India, but some of it is just because you had evolved and developed differently. But in North America and Europe, weird three-wheeled EVs are, have a legacy of failure of three-wheeled road vehicles. Hydrogen trains, hydrogen trucks. Interestingly, down here in the foolish but meh, pipelines are going away, and biofuels, while essential for aviation and road transportation, are going to go away for ground transportation. All ground transportation will electrify. Pipelines, in a world where we are running everything on electrons and getting those electrons to the end ground vehicles as efficiently as possible and putting them into increasingly cheap batteries, as Reggie pointed out, what is the purpose and value of a pipeline? We're not going to be distributing gas. And so one of the things that's interesting is that finally even Germany is recognizing this. And just in the past month, they've acknowledged that gas distribution pipelines to all homes and businesses will not be necessary in the future. There will be no large gas distribution grid. And so they've started planning for the intelligent strategic sunsetting of their gas grid. That's going to take a sub-isolation network by sub-isolation network approach with like a decade or 15 years of shutting it down. This is an interesting place where India is rapidly expanding its gas distribution grid. And it's one of those challenging points because the gas that is delivered that produces clean heat, or not clean heat, but it provides heat that isn't burning biomass, that isn't charcoal, that isn't coal. It's providing food material, it's providing sterilization heat in hospitals. That has value. But as much as you can electrify instead of using gas as rapidly as possible, the better off India will be overall systemically, because you'll be having to decommission a lot fewer pipelines in the future. Right now, I would assert the gas grid is expanding inappropriately rapidly compared to electrifying more things. But over here we have like high-speed rail, very sexy, very practical, electric cars, electric trucks. But down here we have grid-tied trains. As I said, India is getting to 100%. Battery trains are now seeing significant increases in range because it's mostly like shipping, a cost of batteries perspective. There's lots of room on tracks, on trains for batteries, and the rolling resistance is low. The aerodynamic efficiency is high because they're long. And so we're starting to see now 100, 200 kilometer ranges just with batteries. That's completely sufficient to bridge non-electrified segments of certainly passenger rail and regional passenger rail, but increasingly freight rail. Containerized batteries for trains and ships is going to be a big segment in my perspective. Battery trucks, very important in there. Battery transit, which India is doing a very good job on. I know you have plans for 50,000 battery electric buses by 2027. Various international partners have signed off on that. And in context of that, the ISGF, as Reggie has shared with me, and I looked at the white paper, has done a great job of right-sizing batteries for the routes. As batteries get increasingly cheap, that will become less and less important. But still, right now, everybody's attempting to achieve diesel bus range and operational characteristics instead of accepting that batteries are different. And India, at least right now, is doing a much better job of accepting the current limitations of batteries and working around them. Personal EVs, electric bikes, and in India's case, electric three-wheelers. I watched a documentary on the amazing penetration of little electric three-wheelers and the microeconomy of moving people and families around. Fascinating stuff to watch how that has emerged completely, as far as I can tell, without significant governmental support, just because it's a better, cheaper way to do things. Here's the rail situation globally. There is one outlier pair of continents, North America and South America. They just haven't got the rail electrification memo. Meanwhile, India, as I said, is at 94% electrification as of yesterday. And is it targeting 100% this year for heavy freight rail? That's an amazing accomplishment, and I tout that regularly. And India has shown that's doable in a decade and a half. This is not hard to do. Africa is 15% electrified. Morocco and Indonesia both have more high-speed rail than North America does, which is amazing to me. The 9,300-kilometer Trans-Siberian Railroad, which is now being used to carry freight from China to Europe, interestingly, is fully electrified. And so this is the obvious path forward for rail. It's a linear asset. Electrical generation with overhead catenary lines is a linear asset. It makes complete sense, and it's fascinating to think of the reasons why North America refuses to get the memo on this. But let's look at some of the edge conditions of electrification of ground transportation. This is the biggest, one of the biggest mining trucks in the world. The ladder on the side, basically that's a couple of meters off the ground to get to the, getting to the ladder itself is a bit of a hike for most people. And it's an electric truck. In the past year, major mining giants, Rio Tinto, BHP, and Fortescue, have all said, yeah, we're going to make our mines electric. We're going to make all of our mining vehicles electric. It's just more efficient. Hydrogen has no play in this space. So all the edge conditions for biofuels, for synthetic fuels, for hydrogen are dropping off one by one because battery electric and building renewables is so cheap. In Australia, they just recently did something fascinating. They decommissioned a 6-gigawatt solar farm after 6 years. Why? Because they built it for a remote mine. The mine had reached end of life. So they decommissioned the solar farm and they're moving it to another mine to provide solar power for that mine, and thus reducing massively the amount of mining emissions and creating much safer working conditions for all involved, because there's no buildup of diesel fumes underground or for drivers above ground. So now to shipping. There's a story here. So I know Reggie loves this chart. I've talked about it. Shipping is going to diminish, not increase. And this is a heterodox projection, but it's hard to find a reason why it wouldn't be true. Because 40% of bulk shipping are fossil fuels. Big tankers full of oil, or LNG ships full of natural gas, or bulk ships full of coal. Another 15% are full of raw iron ore, going from Australia and other places that have big mines to most of the same ports the coal is going to in China and other places. India has its own massive mining facilities for that. So you're moving a lot more stuff by rail or processing it with coal locally. But that 55% of bulks is going to diminish substantially over the coming decades. We're at peak fossil fuels this decade, and the decline is not going to be immediate, but it is going to be declining decade by decade. And coincidentally, the most egregious fossil fuels are going to be going away first, which is advantageous. Like, sadly for my neighbors in Alberta, in Canada, with their oil sands, that's going to be first off the market because it's highest sulfur, highest CO2 emissions to manufacture, and it's the most expensive to clean up. So container shipping will increase, but it will not increase nearly as much as bulks decrease. And so that makes for a different kind of parameter because those bulks are transoceanic in many cases. And what does that mean? Well, if we think about inland, short sea, and deep water shipping is crossing oceans. Short sea is going from India to the small island off your eastern coast or down the coast of India between ports. All inland shipping and 2/3 of short sea shipping will be battery electric. In 2022, a study was presented that said if battery energy density got the cost got below $100 per kilowatt hour for storage, then routes of 1,500 kilometers were economically viable with almost no loss of cargo capacity. So the economic economic requirement is cheap batteries. And as Reggie pointed out, we're already below $100 per kilowatt hour. And we're going to be down around $50 per kilowatt hour in this year, and probably around $30 per kilowatt hour in 2030. So that means that we'll already be seeing that. As a proof point on this, on the Yangtze right now, there are two 700 container ships that are battery electric, running 1,000 kilometer routes on their inland major river. And they're doing that with containerized batteries. There's that theme of containerization of batteries again, because they just winch the battery containers that are depleted onto shore, where somebody plugs them in, exactly as they do with refrigerated containers today, and they winch a full battery back onto the ship. That's most of these exist in the context of transshipment ports, where trains also arrive. So trains and ships will start sharing containerized batteries as an obvious mechanism for reducing emissions in both spaces. And this significantly reduces our liquid fuel requirements. While I've had discussions with the Maersk McKinney Muller Institute for Maritime Shipping Decarbonization, far too long a name, where they are using 300 to 350 million barrels of oil a year in 2050, 2100 as a requirement for maritime shipping. My projection is only 70 million barrels of oil, million tons of maritime diesel per year. And to be clear, we already manufacture 70 million tons of biodiesel annually. My projection is liquid fuels will be all biodiesel, and there won't be nearly as many of them as we think there will be. And that, by the way, you can see the decarbonization curve there just after 2050. That's real decarbonization, not net zero. Regional air mobility, aviation has a different pathway. So aviation, what we have is the growth of electrification of aviation, just as ferries and other small boats are electrifying now. Smaller planes will electrify first. And the economics and technology are different. We don't care nearly as much about the weight and mass of batteries in ships. We care about the cost of the batteries. In aviation, we need lighter batteries with more energy density. And that's occurring as well. But we need 3 or 4 things to make this work. So one of the things that'll occur is regional air mobility. And I spent time speaking with NASA people who've done the studies on regional air mobility, where the thousands of small aircraft, small airstrips are activated because we have small, cheap, easy to maintain and easy to certify electric aircraft emerging to do cargo and passenger travel between neighboring small airports. Currently, aviation is dominated by hub and spoke airports, where very big jets or bigger jets can do that. Now, as we move forward, we'll need autonomous flight, we'll need digital air traffic control, which is rapidly emerging. Everything has a transponder, and instead of English being the language of air traffic control, computer interfaces will be the language of air traffic control. And battery energy density is increasing already. Just pulling at that battery energy density question, right now with existing Tesla scale batteries, about 250 watt hours per kilogram, and a hybrid model with biodiesel generators on a plane to provide divert and reserve energy for aviation, we can achieve about 98% decarbonization just running on electricity of aircraft up to 100 passengers flying 600 kilometers. And so we have that with just that energy density. But Reggie mentioned CATL, talking about their battery energy, their battery costs going down. Well, they're also delivering this year a battery with double the energy density of the Tesla batteries. So that 600 kilometers becomes 1,200 kilometers. I've spoken to leaders of several organizations which are now building silicon anode batteries, which have the potential to be double or even quintuple the energy density of CATL. There are new chemistries coming out. The implication is that we could have 3,000 kilometer battery only flights with hybrid generators to divert and reserve as an entirely possible viable solution before 2040. And so the implication there is that we have a big wedge for most domestic air traffic that is emerging, and people are just not accepting the obvious curves of these things. To certification, it's much cheaper to certify a electric drivetrain because there's only one moving part. The failure conditions are much smaller on electric drivetrains than they are in current aviation drivetrains, and certification is an N times N safety concern. Now, this is a projected shift of aviation through 2100, similar to the aviation one. COVID caused a significant drop, obviously, in aviation requirements. Recovery from COVID is still not complete. We're still seeing significant pushback on some things. Smaller regional airports have not been able to find staff. The bigger hub and spokes have. Pilots remain a significant problem. A lot of flight crews realized after they got into flying in the 90s because it was great and it was fun and it was exciting. But then when COVID hit and they all had to go find something else to do, they all found something else to do. Many of them didn't actually love their jobs. They just didn't have a way to change. Well, COVID forced them to change, and now we can't get them back. So that autonomy becomes very important because flying a jet is not nearly as exciting as people make it out to be. But as we think about this battery electric 3,000 flights, and in my battery optimistic projection, we'll see transoceanic possibly by around 2070, and then 2100 will have it. In my battery pessimistic projection, we don't get to transoceanic, but still lots. Jet A declines. Once again, it's biofuels. My projection by 2100, even in my battery pessimistic model, is 110 million tons of biofuels required for aviation. With maritime shipping, that's 180 million tons. We already make 100 million tons of biofuels today, and we're barely touching our biomass waste streams. We have lots of room to grow here. This is not even remotely a difficult challenge, assuming my projection of aviation and maritime shipping demand is right. And one thing you'll know is that the growth curve for aviation is quite slow over the coming 80 years. There's 3 or 4 reasons for that. One is we're not going to return to the absurd period of affluence building that we saw from 1980 to 2019. China has gone through that boom and it's flattening out. India and Indonesia and Brazil, while doing great jobs at building their economies, making themselves more affluent, don't have the conditions for success for the double-digit growth rates that China saw, or the markets for things. India, for example, isn't an export market economy nearly as much as China was. And Brazil is exporting dominantly resources and meat, not finished goods and manufactured goods. So the conditions through the coming year are different. Flying for longer hauls will be more expensive because biofuels are going to be more expensive, just not as expensive as synthetic fuels. And battery electric, at least in the short term, will still be challenged by the capital cost of high energy density batteries. So it's a transitional period. Higher cost of flying for the coming next 15 years will depress growth. Lower economic growth and affluence than we saw in the past 40 years, but still growth. We'll see fewer people having the willingness to spend the additional cost for flights. And so I see a much lower growth rate for flying than IATA or Boeing do. Some of this comes down to the question of minerals. Well, when we look at minerals, we have on the fossil fuel side of the world, we're doing about 20 billion tons of extraction, processing, refining, and distributing fossil fuels today, almost entirely for single use, just burning them to create waste heat and carbon dioxide. Oh, and incidentally, some useful working heat for us. But literally, the biggest products of fossil fuels are waste heat and carbon dioxide by multiples. The carbon dioxides are 2 to 3 times the mass of the fossil fuels. And so compare and contrast that to the here's the technology minerals for batteries almost entirely. There's and then here's the industrial minerals for like steel and other things. Now over here, this is 1 million tons. This is 180 million tons compared to and 2.6 billion tons for iron ore, which won't be going up and we'll be scrapping a lot more. But you can see that compared to 20 billion tons, all resource extraction for the minerals required for electrification is a fraction of the mineral extraction for fossil fuels. So that's statement one. If we make this 10 times bigger, it's still a rounding error compared to the fossil fuel volumes. Statement two is when we make put 80 kilograms of lithium into a Tesla battery, that Tesla battery lasts for a decade and is reused over and over and over again, or an electric bus. It's just reused over and over again for a decade. And then once its energy density declines to 80% or so, or its energy capacity to 80%, it will often be repurposed for grid or behind the meter storage as a second life for another decade, and then we'll mine them. And so every million tons of minerals we mine actually ends up being reused over and over and over and over again, and then gets recycled and turned into new minerals. Effectively, because we're achieving greater and greater efficiencies, we actually have not perpetual, but a very, very long lifespan for any of these things, even with degradation through recycling. We also have material substitution. While directly in your wheelhouse, we have the standard aluminum and steel wires for transmission. We have copper, but we also now have reconductoring with carbon fiber and advanced composite technologies inside transmission cables, which are lighter and less heat challenged. They don't heat up as much. They don't sag as much when they heat up. And the combination means that we can actually build HVAC transmission more cheaply with modern conductors. But we can also repower existing transmission with new conductors and get 30 to 50% more energy through the same transmission corridor. And then as we get into other things, we end up getting into the case of subsea cables, where instead of that are lean much more heavily on aluminum for the weight purposes. And so we're starting to see some significant changes there. But all that means is for any mineral requirement, we can use other minerals with similar characteristics. We have lithium ion batteries, but now we're having sodium ion batteries emerging, lithium phosphate batteries emerging. For ground solutions, we're seeing ferrous metal ones. And all this adds up. This is back to the Sankey diagram of actual energy services, the things we care about. So we look at those services, rejected energy plummets in an electrified solution with these wedges I've been describing one after the other. And so we see that we need 27.1 or United States quadrillion BTUs of energy. They waste 6.3. They get a total of 33.5. That's a 56% savings of energy in an electrified world versus a fossil fuel world. Now, that's my calculation. It's napkin sketch math, but let's look at Saul Griffith's work. Saul Griffith went deep and wide on this, and he created the world's most complex and inconceivably inhospitable Sankey diagram, energy flow diagram, down to tiny fractions. In his world, in his calculation, separate from mine, similar methodology, but much more robust, he got down to 42% total energy requirements versus the 100%, which means a 58% reduction in primary energy requirements. Mark Jacobson and team out of Stanford, responsible for 100% renewables by 2050. That evolving set of materials has been going since the mid-2000s, has done similar work and comes up with similar numbers. So multiple people are saying exactly the same thing. Any path where India can electrify now saves significant energy, and any path which India chooses to invest in capital infrastructure that uses fossil fuels is committing India or wasting money on a much less efficient path. And any pathway which uses hydrogen in an energy pathway, whether that's direct use of hydrogen or as synthetic fuel, is going to increase rejected energy, not have their energy requirements for a society. And so the option for India is always, where can you leapfrog based upon existing technology? And this is back to Reggie's point. Cheap batteries means you can leapfrog a lot more. That's my presentation. I've got a few minutes for questions. Reggie, do you want to start sharing the questions? Oops.
That's great. Let me come to some questions. On your third or fifth or sixth slide, there you had written something all that sexy mech slide. One of them written on complete streets. So somebody has asked, could you elaborate on that complete street? So I will stop this. Let Michael come back to his deck. I think it's on the fifth or sixth slide. If we can go back.
Yeah, I'll go back. Come on.
Go up.
Yep.
Yeah. Further.
Is it this one? No.
Yeah,
Next one.
Yeah, somewhere. One of those.
No.
Down.
I went too far. There. Yeah, so complete streets. So complete street is an urban planning concept where streets have, they diminish the space for larger passenger vehicles a bit. So they take lanes away. They create a safe corridor, separated bike paths, separated by parked cars or bollards, where bicyclists and low-speed electric vehicles can transmit in much higher densities, but not have to worry about the safety risks of dealing with passenger transportation. They have pedestrian spaces, and they have trees lining them, so that the trees provide shade for the pedestrians, cyclists, and low-speed electric vehicles who are operating at different speeds. The cars and trucks do not have to interact with slower speed vehicles, but are in lanes which are often optimized for traffic flow. A study out of New York with complete streets found that once a complete street had been implemented, the traffic flow for cars and trucks was slower at peak speed, but the throughput was slightly increased because they move right and left turn lanes out of the primary flow of traffic. So as India's urban areas evolve, complete streets are something to consider. Among other things, the complete street process of putting trees in provides significant urban heat island relief and flood drainage relief. So.
What's your views on bulk versus on-site generation, primarily PV?
So for the one of the key things that is occurring in our energy network is that every geography that used to have to import lots of primary energy can now manufacture lots of its primary energy. in the form of wind or solar. Every geography has, even Singapore has lots of room for solar. It has floating solar, tiny little place, has floating solar on its reservoirs. It has rooftops for manufacturing and its HDB blocks. You can get up to about 15% of its energy demand from local small photovoltaic. That's a very big advantage. Similarly, geothermal heat sources and water heat sources are other sources of local heat or cooling. As we consider those, electricity, as we consider a district, it's easier to justify drilling a geothermal source heat pump for heating or cooling for a district than it is for an individual building. And so we have to think about it more in a neighborhood scale or a district scale in many cases. For most of the world, solar voltaic on domestic rooftops isn't really a huge wedge. And I've had this discussion with Mark Jacobson, simply because most of the world, people live in multi-unit residential buildings, often highly dense. It's true of New Delhi, where Reggie is sitting these days. Very few people live in detached homes as they do in Australia, for example. In Australia, there's a lot of single-story ranch homes, and they actually have more square meters per person of living space than the United States does. So they have lots of room on their roofs for solar panels. Asia doesn't. And where I live, I've got 19 or about 18 buildings over 19 stories of residential, multi-unit residential buildings. We don't have a lot of rooftop for solar either. So it's always a mix. The more you can generate locally, the better, because that reduces the input. But then you can generate a lot more inside a country or a region. And then you have to import a lot less electricity using HVDC or reconductored high voltage AC transmission. And so the entire mix, and you're using a lot less energy in the end space. So the combination means a lot less energy is required to be transmitted long distances than people assume. But major cities like New Delhi are going to require lots of transmission in from all directions as we go forward. So it's for strategies to address renewable energy variability, it's really simple. Broaden the grid, north, south, east, and west, so that you can share electricity from where it is being generated to where it is being used. Electrify everything, so that you've got that. Where you've got demand management opportunities, such as with EV charging overnight, leverage those. And then we have energy storage. I will have a session in this section on grid storage. I'll be talking about pumped hydro. Pumped hydro opportunity is much greater in India near New Delhi than I had realized when I started looking at the material. And so there'll be a fruitful discussion around that. But lots of renewables locally, at a utility scale, transmission, storage, demand management.
So Girish has another question, which I will myself answer. He says, for road transportation, so electrification, how India can ready its aging grid. Our grid is, a portion of the grid is aging, but more grid we are building. We have the newest transmission system. We have the newest distribution system. We given connections to hundreds of millions of homes in the past 10-15 years. Those are all new grid. Well, we have constraint at many places. We will do it as we go along. So in India, it's not going to be a very, very big challenge compared to many other developed places where the grid is really aging and the workforce also aging. So we have both the advantage. We have younger grid, more stable grid, and younger workforce. So that's not a major issue. So
I will add one thing, Reggie, is that an aging grid is less of a concern than most people realize with cheap batteries. Because one of the ways to avoid grid upgrades is just putting a battery at the end of the grid you've got. That's a very buffering batteries for transportation storage, especially for fleets like buses and trucks and delivery vehicles. Putting a battery buffer in means if you've got a weak grid connection, you know it's going to be out for a couple of hours a day, you fill it up when you know you've got grid and you've got some fallback plans. But this is a manageable operational concern, which cheap batteries truly enables. This is not difficult. we can put 3.9 gigawatt hour or 3.9 megawatt hours of electricity in a container-sized battery, a 29-foot container. And that just sits on the corner of a depot or on a parking lot or something. And it's now easy to get. Many organizations are delivering containerized batteries.
Another question is on Nidhi Narayan, the Director of Finance from UPPCL, asking, given the projections for biofuels, will the required feedstock be available?
Yeah, sure. So in projections, we need 180 million tons of them, and we already make 100 million tons of them. So the question is, what feedstocks do we have, and what advantages do we get from using those feedstocks? So right now we have, let's just step back a bit. We have a lot of waste biomass. Currently, we manufacture about 7.5 billion tons of food a year, and we throw 2.5 billion tons of it in landfills. We actually don't eat a full third of the calories we manufacture every year. This is insanely wasteful. And first job is to diminish that 2.5 billion and distribute it better. We have no shortage of food for all the people in the world, or all the people in the world that are coming. The demographic projections are seeing peak population between 2050 and 2070. China's already there. That's why India is now the biggest country in the world by population. Yay, India. And as we look at that waste food, well, all that biomass is stuff that can be put in into either anaerobic digesters, which I don't like, or aerobic digesters with yeast, fermentation, an 8,000-year-old technology, and then into distillation, a 6,000-year-old technology, and then into alcohol to jet or alcohol to maritime diesel processes, which already exist. And we avoid the big problem with that waste biomass, which is methane. All of our waste biomass, from agricultural middens to timber waste, to food waste, to livestock dung, all of that waste biomass, a lot of it creates methane. And methane is a very potent greenhouse gas. And it's going to be priced. It's being priced in the United States right now. It's being priced in Canada. As of 2026, it'll be priced in EU and hence in the carbon border adjustment mechanism for the EU. It's going to be priced in China, which already has a cap and trade solution. And so that methane becomes a cost. Diminishing those biomass wastes, turning them into biofuels, we have billions of tons of waste biomass, and we only need 180 million tons of biofuels. That 180 million tons, we need 1 ton of dried biomass turns into 0.4 tons of biofuels. We have far more biomass than we need. We're just not pricing the negative externalities of methane appropriately. And then, even then, right now, because as we move subsistence farmers off of marginal land, and into cities and into more productive stuff, we intensify agriculture and modernize agriculture. We get more crop efficiency. We have lots of room in the world to grow more fuel crops like rapeseed and canola and those types of things. We can do that in a sustainable way with green hydrogen as the fertilizer. And we have lots of biomass for the requirement. Only if we can persist in burning stuff in every application do we not have enough feedstock.
Good. Kritika is asking, could you provide some numbers or references on how electrification of deep sea shipping on long term compared to fuels like green ammonia or methanol? Those are not used for shipping, but those are carrying green nitrogen to another place. But anyway, electrification more efficient for shipping is the question, long sea shipping.
So in my projection, we'll be seeing biodiesel as the primary energy source for long haul deep water shipping. It's plug compatible with existing bunkering in ports. It's plug compatible with existing engines. We're already bunkering millions of tons of biodiesel for maritime shipping annually every year. It is the ignored stuff. Right now, we make 70 million tons, but we wasted on ground transportation, which we're going to electrify. So that's kind of statement one. But My projection is for long haul shipping is it will be hybrid ships. They'll have batteries, electric drive trains, and reciprocating engines that are generating electricity for the electric motors. The reason for that is inside national waters, that 12-mile limit, is where, and in ports and in movement into ports, and in generating electricity or generating energy for the ports, the ships as they're moored, that's where a lot of port and maritime air pollution, not CO2 emissions, are significantly problematic. And so as I expect that ships will end up in hybrid models, fully electrified in national waters and in ports, and then burning biofuels to power them across oceans, biodiesel. Now, right now, there's a lot of talk about green methanol or green ammonia. They have much lower energy density than biodiesel, 45% or 42% and 45% respectively, ammonia and methanol. Ammonia has very significant health risk concerns, and both of them are going to be more expensive than biodiesel. Green ammonia is going to be 4 to 5 times as expensive as current very low sulfur fuel oil, which is the better stuff that the International Maritime Organization has mandated recently. And it's 5 to 6 times more expensive for specifically synthetic methanol. Biomethanol, there's a pathway to biomethanol from biomethane. Once again, if we capture the methane from existing sources like landfills and stuff and turn that into biomethanol instead of using natural gas to methanol, that actually takes a climate problem and turns it into an energy solution. But it's lower efficiency, it can't be blended, there's a whole bunch of challenges with it. As I said to when I talk to maritime shipping audiences and I talk to people like the Maersk McKinney organization, I consider biomethanol to be the best of the also-ran solutions. Electrification and biodiesel will be the dominant ones, in my opinion. But the study, I'm interested in this because the study said $100 per kilowatt hour or was the price point for 1,500 kilometers of travel. Some of the longest routes are only 15,000 kilometers for ships. And as we consider that, is that a bridgeable gap? How much of the journey can we bunker with electrons instead of batteries? It's something, as I go through this process, I'm going to explore that more. I suspect that my projections for maritime shipping fuels will be leveraging more towards electrons in the future and less towards biofuels. So I think it's an even better story than I thought it was. It's easy to put batteries on ships. They don't have weight constraints and they don't have space constraints nearly as much as airplanes do.
So Narang again asking about the cost of when we electrify everything, the new transmission and distribution lines to be built, if that cost is factored. There are, in my opening statements, I had mentioned about the latest BNEF study of November 2023 that talks about $21 trillion of investment in building about 80 million kilometers of new transmission and distribution lines globally, which is equivalent to, for the next 25 years by 2050. That is to evacuate electricity from the new renewable energy resources which we will be building. It's a very high level 40,000 feet or 80,000 feet study, and each country has several decarbonization or net zero plan which different agencies are making. We need to look into it. It's not going to be a small number, it's a huge number. At the same time, I often say it's a huge challenge and a huge business opportunity for all stakeholders. And somebody else is, you would like to add anything, Michael?
So grid reliability is one of those fascinating things. As we consider renewable energy, I always like to point at Denmark and Germany. They have some of the highest penetration of renewable electricity in industrialized countries. Germany is approaching 60% of all electricity from renewables. That's what it was in 2023. And further, they're electrifying their economies just as India is. They're moving rapidly into electric trucks, buses. They're not as their trains are not as heavily electrified, but their light rail is heavily electrified. And so as we consider that 60%, they also have only 13 minutes of grid outages per customer per year on average. And Denmark is around the same level. Germany often gets over 100% of its energy from renewables. Denmark often gets well over 100% of its electricity demands just from wind energy. Like they achieve 140 to 150% of demand from wind energy. And they share across regions, right? That's part of the reason, that broadening of the grids. The point there is nothing about renewables that diminishes grid reliability inherently. And so it is, and the patterns for more reliable grids are well understood. And some of the new technologies, like the composite conductors for transmission, actually increase grid reliability because in the event of forest fires or extreme heat conditions, they don't sag as much. So you can continue to put just as much electricity through them without concern about them toppling. Further, the new grid technologies, like the composite technologies, are actually cheaper because they're lighter, so you can put the pylons further apart. Fewer pylons for the same transmission distance means a cheaper transmission grid. So we're starting to see significant things. And once again, that behind the meter local storage for buffering is something that wasn't available before. We can store a lot of electricity, and we will be in depots and fleet stores to enable fast charging of buses and trucks. And that increases resilience because those big batteries can be used for local regional resilience in the event of power fluctuations. We're starting to see a much smarter grid down to the distribution level, as well as a smarter grid in the transmission level. Resilience is a concern because of extreme weather events, but it's a diminishing concern with new technologies, new approaches, and greater grid interconnectivity.
Question. Recording of this presentation will be made of the complete recording of this will be available on our YouTube channel, maybe tomorrow or day after it be uploaded tomorrow end of the day. And we had more than 200 people registered for this, although about 50-60 people only attended today. But all the registered people will be sending an email with the link of the recorded version, including the slides, which are uploaded on ISGF YouTube channel. And we have a final question from Kritika again asking, I am sure you have been asked this many times, but do you see a single end-use application where green hydrogen or its derivatives could be a valuable solution?
So the green hydrogen as a solution is a potential. So it is a required solution for ammonia fertilizer. Right now, people I speak to, members of the Hydrogen Science Coalition and others, recognize that hydrogen today, the way we manufacture it, 120 million tons of it a year between pure hydrogen and synthetic fuels. The hydrogen that we use is a global warming problem on the scale of all of aviation. It's in the same order of magnitude. It's like 1.5 billion tons of carbon dioxide or equivalent annually, possibly higher because of findings about the fossil fuel industry's poor record on methane emissions. Dominant pathway, the biggest pathway is turning natural gas into hydrogen. So job number one is to fix that. If we've got a big problem, we don't expand that problem. We have to diminish that problem. And we will, because the biggest single consumer of hydrogen today are oil refineries. Oil refineries need it to get rid of sulfur, to get rid of other impurities, to get rid of excess oxygen, to crack it into lighter and heavier fractions. And so we're not going to be consuming nearly as much hydrogen in the future because that's going down. Now there's other places we use it for, there's projections of expanding it for methanol, but we have biomethanol pathways, which are going to be cheaper. We do need to use it for ammonia. Ammonia is the second biggest. It's about 30 million tons a year, but a full quarter of all ammonia, or of all hydrogen used today, is for ammonia. And we do need ammonia fertilizers. We can't feed those 8 billion people without ammonia fertilizers. So we're going to continue to do that, but we're going to have to green that. Now, the only growth area I project for green hydrogen is potentially in steel and iron under the hybrid process. But even there, electrolysis programs like Boston Metals and Fortescue Mining's don't use They just take green electricity and they use it in electrolysis processes, which can use even dirtier ores than the hydrogen processes can use. So even my extra tonnage, millions of tons of hydrogen for the new steel that I require, remember that 75% of steel requirements by 2100 will be met from scrapping, that 25% of new steel that's required, that's the only place for an upside for hydrogen, and it's at risk of direct electrification through electrolysis approaches. And I know of 2 or 3 now. So I'm suspecting that even that's not a growth area. I don't see any place where green hydrogen as an energy carrier or green hydrogen or its derivatives, like synthetic fuels, makes any economic sense. It's just too expensive compared to alternatives. And because it's too expensive and it's wasteful, why would we do it? Now, there is one place, there's some industrial heat processes where the characteristics of a flame are required for the chemical process. This is small, it's a rounding error on this. Most of them, like ceramics, can electrify, but there's some that just require flame. Will we use biomethane or will we use hydrogen? I think we'll use biomethane personally. It's an easier molecule to manage. It's an easier molecule to capture from landfills and from dairy barns and from other places where there are point sources of methane, and much cheaper to manufacture because we just put it in an enclosed space with a bit of heat and with no oxygen, and the biomass turns into methane. The anaerobic digesters are simple technology compared to electrolyzers, and they're much more robust. So I just don't see a big place for hydrogen. Even in long duration energy storage, I see us capturing waste biomethane streams that we already emit and putting those into existing natural gas strategic stores for countries. And then every decade or 50 years, when we really need some energy, we turn on the gas generators again and we pump the biomethane into the gas generators and get electricity that way. That's kind of like my long-term vision. But everything else, I just don't see a value proposition for hydrogen in any energy pathway. It is an attempt to preserve the existing gas pipeline infrastructure, which doesn't make economic sense. It is an attempt to preserve existing business models for burnable fuels, which doesn't make any sense. Those are not high value, high merit order propositions. People in gas pipeline business, of course, will disagree with me, but oh well, I'm not in the business of making them happen.
One of Michael's paper, he talked about the commercially, commercially launched project. 7.9 million tons of green hydrogen projects are currently under implementation, but the offtake, the committed purchase agreement is for only 0.1 million. 0.1 million. So all others are project announced, financial closure done, some equipment ordered, but nobody knows who is going to buy it. So this 120 million tons of hydrogen which we are producing annually, 99% of it is gray or black hydrogen, which is produced at $1 or $1.2 per kg, and green is not likely to be lesser than $4 per kg even by end of this decade. So that is the reason commercially they are not going to compete anytime soon. So there is another question about battery wastage. We are at 10-15 minutes out over time. We will not get into it. You get a lot of material about what we are going to do with the battery. More of the batteries today are going into mobility application on cars and buses, except and 2-wheelers, 3-wheelers. When the efficiency level comes below 80%, normally they are retired. A retired battery can have a second life in stationary applications like storage, battery energy storage systems, etc., that can serve for another 10 years. So and at the same time, all metals from a lithium battery can be reprocessed or reclaimed, and that technology is fast maturing. And by end of this decade, we expect many of them, the reclaiming metals from the used battery will be cheaper than mining new metals. So it's not going to be a problem. We are convinced about that. Michael, would you like to add anything? We are out of time.
Nope.
Already. Okay. And coming to Arun from UPSLDC is asking any study on pacing electrification industry-wise, geography-wise. Well, a lot of studies are there in every country. Net zero roadmaps are being produced every month by a different agency for every country. So we don't know which each country going to accept and implement. And Ishaji is asking, can you share the answers to the questions separately? So the entire webinar, when we are going to close now, will be recorded, and recorded link will be sent to all the people who are registered, and it will also be available on our YouTube channel. Everybody can access it. It's a free available material. And the next webinar on the series will be on 25th of April, same time. Stay tuned. Thank you very much, Michael. Thank you very much, everybody. And thank you to ISGF team for the logistics, and all the people who joined. Thank you very much. And all the people who sent compliments. It encourages us to do better next time. Thank you very much. Good night. Good afternoon.
Thank you, everyone. Thank you, everyone. The